Hello everyone, I'm Guang Yuli from Tsinghua University. It's my honor to be here to introduce our work, Switches are scanners to a fast and scalable in-network scanner with programmable switches. Let's start this talk with network scanning. Network scanning is a typical procedure to discover active hosts, ports, and services in the network. Currently, it has become a standard measurement technique to understand the security situations of the target network, even the entire internet. Recent studies show that network scanning can help reveal new security vulnerabilities, detect vulnerable hosts, and monitor threat deployment. Obviously, network scanners play a crucial role in conducting such scanning. Today, more and more complex scanning tasks have created new requirements for network scanners. According to Citizen's monthly newsletter, since COVID-19, the frequency of cybercrimes increased 300%. And another report from Improva indicates the duration of network attacks is getting shorter. This demonstrates that security incidents are occurring more and more frequently, and some of them occur in a very small time scale. As a consequence, network scanners should complete a comprehensive scanning as fast as possible, otherwise some important security incidents may be missed. Recently, IPv6 has been in the stage of large-scale adoption, which means increased address space. And along with the deployment of 5G networks, more and more IoT and mobile devices are connecting online. Both of them lead to the much larger scanning space. It means the network scanner should be scalable enough to support current network scanning. However, today's network scanners cannot provide a timely security snapshot and keep pace with soaring scanning space. A closer look into today's network scanners shows they are limited by two factors fundamentally. First, in terms of implementation targets, current network scanners are all implemented on Kubernetes servers. As CPUs on servers are slow for packet processing, the scanning speed of the CPU-based scanners is intrinsically limited. Second, in terms of deployment locations, current network scanners are all allocated at the network edge, where the link has limited bandwidth but need to sustain all the probe traffic. Besides, the long end-to-end scanning path indeed more bandwidth for networks and larger possibilities of packet dropping. So, how to address the limitations? We have a basic but effective idea. That is, in-network scanning, so that scanners can be implemented with high-performance switching ASICs and obtain the huge spare bandwidth and short scanning path from the in-network deployment. But is it possible? The answer is yes. We observe that programmable switches bring unprecedented opportunities to address those limitations. They are specialized for high-speed line-rate packet processing and can also be programmed with domain-specific languages like P4. More importantly, programmable switches provide vantage points to conduct in-network scanning. Therefore, we propose IMap, a fast and scalable in-network scanner with programmable switches. The usage of IMap is similar to traditional network scanners. First, operators should specify the scanning space includes the address list and the port range. The control plane program passes configurations and issues the parameters into the packet processing logics. After that, IMap discipline program generates high-speed probe packets and processes response packets accordingly. The scanning results, that is, the information extracted from the response packets, are read into a persistent database. Finally, operators can query the database to obtain scanning results. The core of IMap includes two models, which we will describe in detail later. Let's see the packet generation model first. The switch is designed to be a packet forwarding device, not a packet generation device. So we leverage a template-based mechanism to generate high-speed probe packets. First, the switch CPU prepares a set of template packets and injects them into the switching ASICs. Then, the accelerator keeps looping these packets in the switch pipeline to achieve 100 Gbps. Some of the template packets will be sent to the replicator, which replicates the template packets into several switch ports. Finally, the editor modifies the headers of replicated template packets into desired probe packets. Nevertheless, to be a practical high-speed network scanner, IMap should cover the scanning space completely and adapt the scanning rate according to network conditions. In the high-speed scanning, simply probing IP addresses in numeric order would overwhelm target networks with scanning traffic. To avoid this, IMap should scan use a random permutation of the address space without duplications and omissions. However, the switching ASICs only have limited memory resources and programmability, which cannot support the address generation approach in CPU-based scanners. To save memories, we design a probe IP range PIPR table based on register arrays, and we also leverage the flexibility of the switch CPU to supplement ASICs. The PIPR entry producer can generate a random permutation of the probe IP ranges and fill them into the PIPR table in order. After that, probe packets can iterate through the PIPR table to obtain random destination IP addresses. When the scanning for the entire PIPR table is finished, the PIPR entry producer should fill a new round of probe IP ranges into the PIPR table. However, filling the PIPR table is a time-consuming task. It means after a round of scanning, we have to wait for the new feeding to start the next round of scanning, which is unacceptable for IMap. To resolve this problem, we introduce two PIPI tables and a rolling filling mechanism. When one PIPI table is being scanned, like T1, the other PIPI table, T0, is being filled with the next round of pop IP ranges. Until now, the design above only considers one port scenario, which should be extended to support a port range scenario. Since the address of pop packets already has good remedies, we choose to scan ports one by one. And because updating the port register from the control plane would bring about risk conditions, we design a port self-increment mechanism in the data plane. When the scanning address space is all scanned, the port register increases by 1. With all the mechanism above, IMap can generate port packets to cover the scanning space completely. To avoid affecting the network, IMap designs a network-aware method to generate high-speed port packets with adaptive rate. The adaptive here has two kinds of meanings. First, the IMap data plane should have one accurate rate adjusting interface, so as a throttle in the switch pipeline, which consists of two registers. The first one is a timer register, used to record the time from the last replicated time packet. The second one is a read register, used to hold the expected time interval between replicated time packets. This register can be specified by the control plane. For every incoming time packet, we compare the values of the two registers. When the timer exceeds the read, we pass the time packet to the replicator and reset the timer. Otherwise, we continue to recirculate the time packets. The second meaning of adaptive is that the IMap control plane should be aware of the network conditions. Thus, it should estimate the network conditions, then determine the scanning rate and update the read register in the switch pipeline. We leave this design as our future work. Then next is the response packet processing model. As an in-network scanner, the input for IMap has both normal packets and response packets, so IMap should first distinguish them correctly. Normal packets will be forwarded according to the original forwarding model. Since the throughput of response packets may be large, IMap needs efficiently process the response packets to avoid saturating the storage server. To distinguish response packets from normal packets, one approach is to maintain a secret state for each packet. However, the switching ASICs only have limited memory. To resolve this, we design a stateless connection mechanism similar to sync cookies. We encode the secret state into the mutable fields of each packet, and these fields also have recognizable effects on fields of the response packets. Especially for TCP scanning, the editor sets SSID port as a hash of key, proto, SSIP, and DSIP, and then sets section number as another hash with SSID port and DSIP port. Accordingly, for received CAC key, IMap has a verifier that checks the DSIP port and ACK number to determine whether it is a valid response to the port packet. One potential issue is that the switching ASICs only support fairly simple hash operations, so attackers may perform chosen plaintext attacks to restore the key, and deliberately inject forged response packets to pollute the scanning results. We leave the detailed exploration of these secret issues as our future work. To avoid saturating the storage server, IMap designs an efficient response packet processing approach. One intuitive approach is to use hash mechanism. However, as the case size in IMap is too large, this mechanism requiring GB memories is not feasible. Instead, IMap adopts a response packet aggregation mechanism. More especially, IMap designs a dedicated n-size register array to temporarily store the scanning results. During the scanning, the information extracted from the ith packet will be stored in the ith register. When the register array is filled up, the certain response packet carries all the results in the register array and goes to the storage server. Meanwhile, the counter is reset at 0 and another aggregation loop starts. For evaluation, we implement the prototype of IMap on a real physical Torino switch. To set up our experiments, we have two servers connected with Torino switch. One runs as a node to bridge IMap with our campus network, and the other one runs as a storage server. Finally, we conduct preliminary experiments to show the performance of IMap. As you can see, IMap is able to generate port packets at 40 Gbps, which is a 4 times improvement compared to ZipZMap. Note that 40 Gbps is not the upper limit of IMap. When IMap scans at 40 Gbps, several edge networks in the scanning space only receive hundreds of port packets per second, which is negligible for most edge networks. To conclude, we identify the limitations of current network scanners, propose a fast and scalable in-network scanner IMap, and implement the prototype of IMap. In our ongoing work, we are planning to improve the design and implementation of IMap and conduct extensive experiments and measurements. That's all. Thank you. I'm happy to take any questions.